The next piece of the review that we need to talk about is the scientific method, and we can look at the scientific method as being a scaffold upon which all scientific discovery, including discovery within chemistry, is performed. So when we look at the scientific method, it has a number of steps, and most people are familiar with the steps, but what we don't notice, or what some people don't notice, is that it actually represents a cyclical process. The first thing that you have to do is identify a problem. You make an observation which leads you to ask a question. I look outside the window and I see that the grass is greener on one side of my lawn than on the other, and that causes me to ask a question. Well, why? Why is it like that? From that observation or that question, I form an educated, tentative explanation, a hypothesis that explains potentially the question. So I might hypothesize that, well, my grass is greener on one side of my lawn because it gets more water than on the other. Once you have a hypothesis, scientists create an experiment, and that experiment really is used for the process of making observations, collecting data. Once we have those observations and the data, we hope to be able to create relationships, and that would allow us to draw a conclusion. This is normally the stopping point that people anticipate in the scientific method, but it's not. Because what we see is that when the scientific method is employed properly, those relationships cause us to make future predictions, which again lead us back to repeated experimentation, which allows us to test the relationships or reform the relationships that we've had, and so on, back to make more predictions. If you can repeatedly follow that cyclical process and repeatedly get the same results, we may be able to create one of two things: a natural law or a theory. We'll talk about a theory first because most people are more familiar with or have heard that term more than the law. So what we see is that a theory is a hypothesis which has been repeatedly tested and here's the important part, repeatedly been shown not to be false. It's not necessarily that a theory is true. Instead, it's that it is not false based on the evidence or the data that we've been able to collect till this point. Most people have an understanding of that when you look at theories such as the theory of evolution. Is it that the theory of evolution is true? No, most scientists would acknowledge that it is not necessarily true. It may be, but it's not necessarily. What the theory of evolution is a hypothesis which has been repeatedly tested against a set of observations, against a fossil record, and has been repeatedly shown not to be false. In contrast to that, when we look at a natural law is a physical reality. It is never disproven or never false. You can never disprove any physical law. The law of gravity is a physical reality. One body, a smaller body, will be naturally attracted towards a larger body by the force of gravity. When we look at the law of conservation of mass or matter is neither created nor destroyed in a normal chemical or an ordinary chemical or physical process. It only gets changed from one type to another. Those laws are never violated. So when we come to doing these experiments, we obviously have to make observations. So observations can actually be described as being the basis of all science. And they can be broken into one of two kinds. There are qualitative observations, which deal with properties that don't need a number. These are things like state, is it a solid, a liquid, a gas, is it a color, is it an odor? These are things that you can observe, things that you can notice or see or smell, a texture, but they do not need or have a number associated with them. On the flip side, we have quantitative properties that deal with values and have to have an associated measurement with them. Density, mass, the size, the temperature, anything that you can make note of or things that you can observe that has a number attached to it is a quantitative property. It's interesting to note that when we look at qualitative properties, color for example, some of those qualitative properties can actually be, using the proper tools, turned into quantitative properties. So to enhance our powers of observation, we use instruments which help us to make our observations or make them better. Things like the electronic balance, thermometers, graduated cylinders, even things as simple as the meter stick. And what you need to recognize is that when we look at these instruments, all instruments are based on measurements that are comparisons to universally accepted standards. When I look at a meter, well, what is a meter? People will say 100 centimeters. Okay, well then what is a centimeter? People will then say, oh, well that's 10 millimeters. Okay, well what is a millimeter? Well, there are 1,000 millimeters in a meter, a cyclical reference. So when we look at these, a meter is a meter because someone arbitrarily defined a meter to be so. I know that it has something to do with the diameter or the circumference of the Earth through some point in France, but that's not important as the fact that someone had to decide that that's what we were going to call a meter. When we look at a measurement, it describes a quantity, and a quantity has to have both a number and a unit that names the standard that was used. So 50 centimeters, 20 kilograms. In science, with very few exceptions, any number that you write down as a measurement must have an associated unit. A couple of exceptions would be a magnification in biology or the coefficient of friction in physics, but really with very rare exception in science, any measurement or any quantitative property should have both a number and a unit. When we look at the units, these are things that are based around the metric system, the System International, SI units, and we have already talked about the metric system and its importance. So derived units were developed in order to allow scientists to gather more meaningful quantitative observations about their surroundings. They're derived by using combinations of other units, meters per second for velocity or speed, newtons per meter squared, which is a measure of pressure. One common unit derivation that we see in chemistry is density, and density is a measure of how much matter, in other words, the amount of mass that's contained within a given volume. And as a result, it commonly has units of grams per milliliter. So once you've had your hypothesis, you've made some observations through experimentation, the next step is to potentially draw relationships. So what we see is that the purpose of experiments is to seek regularities in our observations in order to develop meaningful relationships. And this can be done in several different ways. We can use mathematical equations, we can produce models, and we can make classification schemes. When we look at mathematical equations, we need to gather data from measurements, and most commonly, we will graph that data so that we have a visual representation of the connection between two different variables. When we look at models, models help us to understand or visualize a concept. And they can potentially use different scales for an object. So we can make a model of what the atom would look like, even though it's impossible at this point for us to see that. From an engineering perspective, you can take a scale and replicate the conditions that something that would be very expensive to produce, such as a bridge. A classification scheme is one of those things that lots of people don't actually realize they're using, but have used all their life. And what they do is they organize large collections of objects, ideas, or things into smaller groups based upon common properties. And a good scheme includes the following properties. 1, everything has to fit within it. There can't be any overlap between them, and it has to be easy for everyone to use. And a good example of this is the library. So if you were to go to the library, it includes all the objects, includes all the books that you would like to have in the school. Relationships allow us ultimately to make predictions, which in turn are tested for making future observations. And as we said before, if a relationship holds true after repeated testing, it's been repeatedly been tested and repeatedly been shown not to be false, then it could become a theory if it can be used to accurately explain past and present events and to predict ones that will happen in the future. So if a prediction is not true, that doesn't necessarily mean that you should throw that out. Instead, maybe it's necessary that you need to make more observations. Perhaps you need more detail to make the observations with. Or, on the flip side, you don't necessarily have to throw out the relationship, but maybe you need to reevaluate it or reevaluate the hypothesis and change the parts that don't fit it anymore. So let's do a quick review of the cycle. So the first thing we did in the cycle was to ask an initial question. And that question was based on an observation. From that observation, we formed a tentative explanation, an educated guess to explain it. That is our hypothesis. Once we have our hypothesis, we would like to make observations through experimentation. So that's our experiment. And the purpose of those observations is hopefully to create relationships, to see things that are connecting one property to another. My grass is greener over here because yes, it had more water than on the other side. Once I have those relationships, I need to again make predictions. I need to test those repeatedly. And that will lead us to more observations. If the relationships are consistently been found to be true, we may be able to make a theory or a natural law. So those are the foundations of the scientific method. We'll be looking at how to incorporate those methods and doing an activity that revolves around the importance of classification schemes in particular next day in class.